We're now going to consider time dilation. So just as two different observers in different inertial reference frames don't agree on the length of an object which is moving relative to one of them, they also don't agree on the interval of time between two events which they observe from their respective reference frames. So to show why this is, let's start by considering a light clock. So in a light clock, we've got a source of light. The light is shone up to a mirror and reflected back down to the source. And the clock goes on when the light is first emitted from the source, and it goes off when the light returns to the source. So we will consider observing this light clock from two different frames. So first of all, let's consider the S prime frame. So this is inside a rocket ship. And in this frame, the source does not appear to be moving. So let's calculate how long would it take the light to go from the source to the mirror and back, and we'll assume that our rocket ship has a height d. So in this case, the light has to travel a distance d up to the mirror and then a distance d back. And so the total time it takes to do that in the primed frame, so t prime, is equal to 2d, the total distance, divided by c, the speed at which light travels. So we can call this time to, the rest time, because this is the frame at which that clock, the source, is at rest. Now let's consider observing the same clock from a reference frame S outside the rocket. So in reference frame S, it looks like our whole rocket is moving to the right with speed u. So the light is emitted from the source, but then the source is moving horizontally and the mirror is moving horizontally. So it travels along a diagonal path up to the mirror, and then when it gets to the mirror, it's reflected back to the source, and by the time it gets to the source has moved a distance ut, where t is the time between when it was emitted and when it is observed. So let's try and come up with an expression for this t. So to do that, we'll need to start by working out, well, exactly what distance has that light travelled. Well, we can see from symmetry that it's travelled the same distance on the way up to the mirror as back. So we just need to work out the length of one of those sides, and then we can double it. So to work out the length of one of these sides, we can just use Pythagoras' theorem. The height, the vertical distance, is given by d, and it takes half the time for it to get to the mirror. So the distance the mirror has travelled in that time is given by u times t on 2. So the total distance that the light travels to the mirror and back is given by 2 times the square root of ut on 2 all squared plus d squared. Now let's make that a bit neater by putting the 2 inside the square root sign. When we do that, we multiply inside the square root sign by 2 squared, which is 4. So that gives us that the time t is equal to u squared t squared plus 4d squared. So now we can work out the time. The time is equal to the distance travelled divided by the speed, which is c. So we've got t is equal to the square root of u squared t squared plus 4d squared divided by c. Now we've got t on both sides, so let's just square everything and multiply through by c. So when we do that, we've got c squared t squared is equal to u squared t squared plus 4d squared. We'll put all our t terms together. So we've got t squared times c squared minus u squared is equal to 4d squared, which we can rearrange to t squared is equal to 4d squared divided by c squared minus u squared. But what we're trying to get is t, so we will take the square root and we end up with t is equal to 2d over the square root of c squared minus u squared, which is pretty good. But let's just divide we'll move a factor of c out of the c squared outside the square root. So we can write this as 2d divided by c times the square root of 1 minus u squared on c squared. And why this is nice is we can now relate it to the rest time, because the rest time was given by 2d on c, so this is equal to t0 divided by the square root of 1 minus u squared on c squared, or if we want, t0 times gamma. So what this is telling us is that the light appears to have taken longer to go from the source to the mirror and back to the source in the frame in which that source, the clock, is moving. So this is known as time dilation, as it appears that the time goes more slowly in the frame which is moving relative to us. Now, you have to be very, very careful with how you apply this time dilation equation. You may have noticed that in the example we were talking about in the rest frame, that light returned to the same position from which it started, and that is actually really important. So let's have a look at another way we can derive this time dilation equation now, using the Lorentz transforms, just to show why it's so important that in that rest frame we're considering something which is returning to the same location. Okay, so to do this we're going to need to use our Lorentz transform, that t prime is equal to t minus ux on c squared over the square root of 1 minus u squared on c squared. Now, it's always useful to have a really clear diagram about what's going on in our two different frames. So here's our S frame. In our S frame, we've got the rocket here, which is moving this way with speed u. We're observing the light. So the light starts here at the source, it's reflected off the mirror, and then comes back to the source. So the light looks like this. Now let's label up the important coordinates in this S frame. So we can call this position XA, this is where the light starts from, and then when it gets back to the source it is at a displacement XB. Now let's draw on our S primed reference frame, so that's inside the rocket ship. So we can draw the axes as along the rocket ship here. So this is the S prime frame, which is moving with the rocket ship. So in the S prime frame, the light travels up and then back. And so labeling this location, it starts at XA prime and it comes back to exactly the same location, XB prime. These are the same. Now, what's a bit hard here is that we are trying to get the time t in the S frame. And here we've got a transform which, if we knew t and we knew x, we could get t prime, but it's not actually the other way around. What we have is t prime and x prime, and we want to get t. So how do we go about doing that? Well, there's a hard way and an easy way. The hard way involves looking at this equation and looking at our other Lorentz transform for x. X prime is equal to x minus ut over the square root of 1 minus u squared on c squared, and we can solve these simultaneously to come up with some expression for t. But that is really quite challenging. So there's actually a much easier way. What we can do is, well, imagine that we are in frame S prime, and this is our reference frame, and we want to envisage how the reference frame S is moving relative to us. Well, when we're in the rocket ship, it looks like the frame S prime is moving back this way with speed u. So equal and opposite speed to what we are observed with from frame S. So what we can do is consider this transform, but now we're transforming the other way around. So what we mean by that is, well, that's t prime is going to become t. This is going to become t prime, but this speed is in the opposite direction. So the minus u becomes a plus u, and the x is the x prime on c squared, and then this is over the square root of 1 minus. Now, because this u here is squared, it doesn't matter that it's a minus u, because minus u squared is the same as u squared. So that's still u squared on c squared. So just using physical arguments, it's simpler to come up with this expression than just using these two expressions here, but both can be done. So now we've got an expression for how to relate t to t prime and x prime. So we can write, well, t, we're trying to measure the time between these two events here. So we want TB, that's our final time when it gets back here, minus TA, that's the initial time when it's released, is equal to TB prime, that's when it gets back to this mirror, plus UXB prime on C squared over the square root of 1 minus U squared on C squared, minus the initial time, which was TA prime plus UXA prime on C squared over the square root of 1 minus U squared on C squared. So this is equal to TB minus TA prime prime plus U times XB prime minus XA prime on C squared over the square root of 1 minus U squared on C squared. Now, because XA prime and XB prime are the same, this term here is equal to 0. So we can replace this with 0. So U times 0 divided by C squared is just 0. So this gives us the final expression. This is equal to TB prime minus TA prime over the square root of 1 minus U squared on C squared. And TB prime minus TA prime, that was just the time between these two events in the rest reference frame, the primed reference frame. So this is equal to T0 over the square root of 1 minus U squared on C squared. So you can see this is just the equation that we got for time dilation before. But now you can see explicitly that we had to assume that these two events occurred at the same location inside that rest reference frame. So this is not always the case in every situation. So do not apply the time dilation formula blindly. Ask yourself, are these events occurring at the same location in one of the frames?